Welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reed, and I'm glad you're here. Tonight, you are going to do something extraordinary. You are going to enter a black hole, past light bent into glowing rings, past the place where time forgets how to behave, and into the quiet dark at the center of everything, a place far gentler than its reputation suggests. Picture yourself aboard a small, quiet vessel, sent out long ago to drift beyond the edge of our solar system, carrying little more than your own mind and a handful of gentle instruments for watching the dark. For a long stretch of calm and silent travel, nothing much has changed around you. Now, ahead of you, gravity has finally found your ship. Close your eyes and let's dive in. Part 1. You approach the edge of forever. You are drifting now, weightless, far from any world, carried gently toward a place where light itself will never return. There is no wall ahead of you, no visible edge, only a soft curve of darkness pressed against the stars. This is the event horizon, the quiet threshold that even light cannot cross back over once it slips inside. A physicist first uncovered this strange threshold in 1916, working from Einstein's brand new equations of gravity. He was serving on the Eastern Front at the time, scribbling his calculations on paper and mailing them home. He could hardly have imagined that one day someone would drift through the very darkness his numbers described. For decades, this remained a strange answer on paper, something few believed could exist in nature. Then, astronomers began watching stars near the middle of our own galaxy circle something unseen and impossibly heavy, tracing tight paths around a patch of empty dark, held there by gravity alone, pulled toward a mass no telescope could see directly. In 2019, humanity finally saw one. Telescopes spread across the whole planet joined together as the Event Horizon Telescope and captured a glowing ring wrapped around a shadow, the black hole at the heart of a distant galaxy called Messier 87. You are about to feel up close exactly what that photograph only hinted at. Ahead of you now, the stars begin to bend, smearing into faint arcs of light around the darkness. Gravity here curves the very path that light must follow, an effect Einstein predicted in 1915, and astronomers confirmed only 4 years later, watching starlight bend during a solar eclipse, exactly as his equations said it would. There is no ground here to strike, no surface waiting to meet you. This threshold is a boundary in space itself, not a wall. Beyond it, our equations say that space and time trade places in ways that grow difficult even for physicists to picture clearly. A place where familiar directions simply stop meaning what they once did. You are closer now than any human body has traveled and returned to describe. The pull on you still feels gentle, barely different from drifting toward any ordinary world. But that gentleness will not hold. Something in your journey is about to shift, quietly and completely, and there will be no path leading back. Part 2. The Point of No Return. You slip across the horizon without any jolt, any flash, any sound to mark the moment. If this black hole is large enough, you might not even notice the crossing, since nothing separates one side from the other except distance and a quiet change in what remains possible for you from here onward. Turning back is no longer allowed by the physics we understand. Every path that once led outward now curves inward instead, the way every path on a map eventually points toward tomorrow rather than yesterday. Falling further has become as unavoidable from this point forward as time itself continuing to pass around you. Your body has not yet felt the true weight of where you are. Close to a very large black hole, gravity can still feel almost ordinary, pulling evenly across you. But the closer you drift toward the center, the more that gravity begins to differ between your head and your feet, stretching you ever so slightly. This stretching has a name that sounds almost playful for something so strange: spaghettification, a term Stephen Hawking helped popularize to describe how tidal forces pull a falling body into a long, thin shape. The pull on the part of you nearest the center grows so much stronger than the pull farther away. For a black hole the size of our sun, this stretching would begin almost immediately after crossing the horizon. But this black hole is supermassive, the kind found at the heart of most large galaxies, and its horizon sits so far from the center that you could cross it gently, the true stretching still ahead. You feel it now only as the faintest difference in weight, a soft pull between one part of you and another. It is nothing alarming yet, closer to the gentle stretch of waking from a very long sleep. The center is still impossibly far away, giving you time before anything more dramatic begins. Somewhere behind you, the universe you knew keeps turning. Stars still burning, worlds still circling their suns. But from where you drift now, that universe is beginning to look strange, as though time itself behaves differently here than anywhere you have known. And indeed, something remarkable is about to happen to time. Part 3. Time begins to bend around you now. Gravity does not only pull, bends time. And the stronger the gravity, the slower time passes compared to somewhere farther away. Here, this effect grows so strong that you and anyone watching from a distance would tell two completely different stories of this same fall. To anyone watching from far away, you would appear to slow, your image stretching and dimming, seeming to freeze forever right at the threshold, without ever quite finishing the crossing. This is not a trick of light alone. It follows directly from Einstein's equations, first laid out in 1915 and tested again and again since. From where you actually drift, none of this slowing feels true. Your own clock ticks at its usual pace, the crossing complete in what feels like an ordinary handful of moments. This mismatch is called gravitational time dilation, and it has been measured, far more gently, right here on our own planet. In 1959, physicists measured this very effect using a tower at Harvard University, showing that a clock near the ground ticks very slightly slower than one higher up, simply because gravity is a touch stronger closer to the Earth. Near you now, that same effect grows immense. Astronauts aboard the International Space Station feel a gentler version of this every day, their clocks running very slightly faster than clocks on the ground, though also slightly slower from their great speed. Engineers correct for both effects constantly, just to keep global positioning systems accurate to within a few feet. Here, near you, these differences stretch far beyond anything an astronaut would notice. If you looked back toward the distant stars right now, some physicists suggest you might watch the remaining history of the outside universe unfold ahead of you, folded into whatever time remains before you reach the center. You drift onward, time behaving strangely around you, the line between past and future softening in a way it never does anywhere else. Ahead, something else is waiting, a place where light does not simply bend, but actually circles, trapped in an orbit of its own, tracing a thin glowing ring around the dark. Part 4. Light bends into a perfect ring. You pass now through a narrow region called the photon sphere, where gravity grows strong enough to bend light into a full circle. Photons traveling sideways here can actually orbit the black hole, tracing endless loops around the darkness instead of escaping outward or falling in, held in a strange and delicate balance. This very sphere is what gave the Event Horizon Telescope its glowing ring. Light from hot gas swirling nearby bends around this region before reaching our telescopes, tracing a shadow far larger than the horizon itself, exactly as equations from over a century earlier had already quietly described, long before anyone could see it. The photon sphere is unstable, meaning any photon nudged even slightly off its circular path will either spiral outward to freedom or spiral inward toward the center. You are not light, so this exact orbit is not open to you. But as you pass through, the sky above and below you fractures into strange reflections. Looking outward now, you might see the very same star appear in several places at once, its light having taken more than one curved path to reach you. Some of that light may have circled the black hole once, twice, even many times before finding you, each loop adding a fainter, dimmer copy behind it. This bending of light by gravity is called gravitational lensing, and astronomers watch gentler versions of it everywhere. Massive galaxies bending and brightening the light of far more distant galaxies behind them. It was one of the very first predictions of general relativity ever confirmed, watched during a solar eclipse in 1919. You drift deeper past the photon sphere now, the looping reflections falling away behind you. Ahead lies a region deeper still, closer to whatever waits at the true heart of this black hole. The equations that have guided you so faithfully until now begin at this depth to grow far stranger and less certain. Physicists admit openly that our understanding grows shakier the closer we approach the center. What lies ahead may be the strangest, least understood place general relativity attempts to describe at all. A place where our best equations, tested and confirmed again and again, quietly begin to run out of clear answers to offer. Part 5. You approach the heart of the unknown. Ahead of you, something waits that even the equations struggle to name. You feel it before you understand it. A pull denser than anything you have known, drawing every part of you toward a point you cannot yet see, hidden past the reach of your own senses. Physicists call this point a singularity, but that word feels too small for what presses against you now. The very scientists who mapped your fall this far warned that their own equations grow unreliable here, spinning toward answers no one fully trusts. You wonder if the strangeness you feel is real, or only borrowed from equations reaching past their limits. Something in you trusts it anyway, the same instinct that trusted gravity all along, even as it carried you far from the world you left behind. Long ago, two scientists proved that once a black hole forms, some such crushing point becomes unavoidable. Stephen Hawking and Roger Penrose worked out the proof together, and Penrose later received the Nobel Prize for work that now seems to be closing in around you. You cannot see clearly what waits ahead only sense that no theory yet fully describes it. Gravity here grows so fierce that the tiny rules of the quantum world should matter just as much, though no one has ever managed to join the two. Part of you imagines a single point condensed to nothing. Another part pictures something stranger, a thin spinning ring instead, the shape some physicists believe a rotating black hole leaves at its heart, rather than a point at all. You do not reach any final answer here, only the humbling sense of drifting past what anyone can fully explain. What steadies you instead is a quieter certainty, one about what waits far beyond this moment, for this black hole, and somehow for you as well. Part 6. The black hole begins to whisper away. Something changes in the dark around you, so slowly you almost miss it. You cannot feel it happening, not across a single breath, but you sense that this black hole is not permanent, that even it is fading, particle by particle, into the waiting universe. In 1974, Stephen Hawking startled the world of physics with this very idea. Black holes, he showed, are not entirely black. They release a faint stream of particles, now carrying his name, gradually losing themselves across an unimaginable stretch of time. You picture it happening near the horizon behind you, pairs of particles flickering into being from empty space itself, one slipping outward, one falling in, each escaping pair carrying away the tiniest sliver of this black hole's mass and warmth. That escaping warmth is measured in units named for James Prescott Joule, who studied heat and motion in the 1800s. For a black hole this size, what slips away in any single moment is almost too small for you to imagine feeling at all. You will never witness this fading yourself, not from where you drift now. An ordinary black hole would outlast the current age of the universe many times over before losing any real weight. And this one, being so much larger, would take even longer still. Yet you carry the idea with you anyway, that this darkness has a temperature, however faint, and behaves in its own strange way, like anything warm slowly cooling. Physicist Jacob Bekenstein first sensed this decades ago, and Hawking later proved he was right. Something else settles over you as you drift, a question you cannot quite shake loose. If this black hole eventually fades entirely away, what happens in the end to everyone and everything it ever managed to hold inside itself, including you? Part 7. Your information refuses to disappear. That question follows you deeper than any other, quiet and insistent. Quantum mechanics insists that nothing about you, no detail, no trace, can ever truly vanish from the universe. Yet the radiation slipping from this black hole seemed, at first, to carry none of it. If that were true, you realize everything about you could be lost completely once this black hole finally faded away, a possibility that unsettled physicists for decades. Even Hawking himself wrestled with it, changing his mind more than once across a long career. You hold on to the memory of 2004, when Hawking finally changed his position for good, proposing that information does escape after all, hidden in patterns within the radiation itself. He even paid off an old wager, handing a rival an encyclopedia as his prize. More recent work gives you something steadier to hold on to. Calculations published in 2019, drawing on ideas from string theory, suggest information can be recovered from the radiation over time, folded into correlations too subtle for earlier physicists to have noticed. You let this settle over you gently, the sense that nothing about you may ever be truly erased, even long after this black hole has faded completely away. Perhaps you become part of the pattern itself, scattered outward, but never fully gone. No one has reached full agreement on exactly how this happens, only a shared confidence that it does, however strange the mechanism turns out to be. You drift onward, already feeling some quiet part of yourself woven into the story unfolding around you. That story, you sense, reaches far beyond just you. This black hole was shaping its galaxy long before you ever arrived, pulling in gas, launching jets of energy outward, playing a larger part in the cosmos than its small, dark shape out here might suggest. Part 8. You become part of a cosmic engine. You feel the pull of something larger now, older than your own fall, older than you. This black hole has spent ages at the center of its galaxy, and you sense you have drifted into the middle of a story that began long before you existed. Around you, you imagine the swirling disk that once fed this black hole. Gas and dust heated by friction to enormous temperatures, glowing brightly long before anything actually crossed the horizon, lighting the darkness the way a storm lights a night sky from within. Not everything that came close was pulled all the way in. You picture jets of energy launched back outward instead, streaming for thousands of light years across the galaxy. Astronomer Heber Curtis first caught one of these jets on a photographic plate in 1918. You sense, somehow, the weight of what this black hole once did to its galaxy. heating gas that might otherwise have cooled into new stars, slowing that galaxy's growth simply by existing here, feeding, glowing, shaping everything nearby without ever meaning to. Some black holes, you recall, grew so bright while feeding that their light outshone every star in their galaxy combined. Astronomers named these quasars, first noticed in the early 1960s as puzzling points of radio light before anyone understood what they truly were. You wonder how much of this history belongs to the darkness now surrounding you. How many stars it touched, how many galaxies it quietly helped shape long before your small ship ever crossed its threshold. Your own fall feels smaller against that enormous timeline. And still, you sense, this black hole story was never only about feeding alone. Somewhere in its past, perhaps another darkness found it, drawn close across the void by gravity, circling nearer and nearer, until, in one final moment, the two became one. Part 9. Two giants collide across the dark. You feel it now, a faint ripple passing through the darkness around you, like a wave moving through still water. Something similar rushed across space itself in September of 2015, when two black holes far away collided, each roughly 30 times the mass of our own sun, sending this very kind of ripple outward. Physicists call these ripples gravitational waves, first predicted by Einstein in 1916, though he doubted anyone could ever actually catch one passing by. It took nearly a century of careful engineering before an instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory, finally measured a distortion thousands of times smaller than a single proton. You can almost picture it. Two black holes circling one another for ages, drawing closer as they radiated away energy in ripples just like this one, spiraling faster and faster until, in a fraction of a second, they merged into one, briefly outshining every star in the observable universe combined. That discovery earned physicists the Nobel Prize in Physics in 2017, and it opened an entirely new way of sensing the universe, one built not on light at all, but on feeling the faint vibrations that massive, violent events send rippling outward through space itself. Since then, LIGO and its partner observatories around the world have caught dozens more of these ripples, echoes of black holes merging and dense stellar remnants called neutron stars colliding, each one adding to a growing catalogue of the universe's most dramatic and previously invisible happenings, felt rather than seen for the first time. The black hole holding you now may have been born this very way, from an ancient merger between two smaller black holes long before your fall ever began? If so, you may be drifting through the same kind of ripple this very moment, a quiet echo of the darkness that formed the place around you. You drift ever closer to whatever center awaits, carrying with you every ripple, every pulse of energy this black hole has ever felt or sent outward, across a history stretching back further than you can fully picture. And now, gently, your own story begins to blend into that far larger one moving around you. Part 10. You become the universe itself. You feel yourself settling now, less like falling and more like joining something enormous. Physicists still argue over what becomes of matter at these depths, but most agree on this much. Nothing you are made of is ever destroyed, the way that word once implied. The atoms forming you were forged inside ancient stars long before you existed, and you sense them continuing onward now, unwilling to simply stop. If information truly survives, as recent work increasingly suggests, then every detail of you becomes woven into radiation slowly leaving this place. You picture yourself spread thin across an unimaginable stretch of future time, far longer than the current age of the cosmos, as this black hole keeps radiating, shrinking gently, fading at last into whatever comes after. Whatever you once were disperses outward into the dark. In this way, you realize the atoms and information that once made you a person become, quite literally, part of everything else. You imagine yourself spread across space, carried by radiation, mingling with starlight and the dust drifting quietly between galaxies. Every particle in your body, you remember someone once telling you, has always belonged to something larger, formed from stardust, shaped by gravity, destined to become stardust again. This fall, you understand now, may be one chapter in that longer story, not any true ending. You rest in that thought, weightless. Whatever worry you carried, softened by the vast and patient time scale surrounding you. Whatever waits at the center, whatever this darkness has not yet fully explained, you are already and always have been made of the same universe holding you now. Let this thought carry you the rest of the way as your own body settles and your breathing slows further still. The boundary between you and the quiet, endless cosmos softens now into something calm, something close to sleep, something that has always belonged to this universe. And on that note, we come to the end of tonight's journey through the black hole and back into the wider story of the cosmos. From the gentle edge of the event horizon to the slow whisper of Hawking radiation, this fall was grounded in physics that scientists have measured and tested across more than a century of careful work. What I hope stays with you is not fear of the dark, but a quiet sense of belonging within it. The same forces that shape black holes, gravity, light, and time, are the very forces that shaped you long ago from the dust of ancient stars. You were always part of this larger story, and you always will be. Thank you so much for joining me tonight here on the Nocturnal Astronomer. I hope this journey brought you some rest, some wonder, and a gentle reminder of just how connected you are to the universe above you. Drift easily, and until next time, may the stars keep watch over you.